Hello everyone, welcome to this one-shot review of AP Calculus AB as well as BC. We are in Unit 4, Contextual Application of Differentiation. In this video, I will be breaking down the key concept and work through the essential examples. This will help you master problem-solving techniques for real-world applications. If you are preparing for a test or if you just need a quick refresher, this will be the right video for you. So let's get started. The first subunit is interpreting the meaning of the derivative in context. So a basic prerequisite is this is what required. If your function is f of x and the first derivative is denoted by f dash of x and second derivative is f double dash of x. We will deal with these things. And yeah, we have to learn some techniques how to interpret them. That's all about it. Now let's have some general view of physical context. First thing is physical and velocity. So how velocity is like we are going to represent in the form of differentiation is if s of t is a representation of a position as a function of time, then s dash of t, the first derivative of the position function, gives you velocity. And acceleration, same. If s of t represent position as a function of time, then s double dash of t will give you acceleration. Otherwise, s of t represent a function of time. What if you don't have position, if they give velocity, then v dash of t will give you acceleration. This is all about physical context. A lot more context is there. Economic context. So the best example is marginal cost. If C of x represent total cost of producing x units, then the first derivative will give you marginal cost. Marginal cost means like if you want to produce one extra unit, you produce 5 units, and then you have to produce one extra unit. The 6th unit means what is the cost. So that is what this marginal cost will give, and C dash of will be the one which represent the marginal cost. And also revenue or profit. Revenue or profit is the derivative which tells the rate in which the revenue or profit as the production level change. At some production level, there will be a profit increase, the profit decrease. So this is the context in economic. And biological context, the population, growth rate. So if P of t represent population at time t, P dash of t represent growth rate. And what we need to understand while you're take care while you're interpreting the derivative is identify the variables, determine what is dependent and independent variable and what they represent. And next, understand the units. Unit is very important. Like pay attention to the units of measurement for both the variables. Like one will be in meter, other will be in second, one will be a temperature degree Fahrenheit, other will be in minutes. So, and we have to interpret them in a proper order, and you will get it while we are solving examples. Then, interpret the sign. Yes, we will get some number, like if you are interpreting a derivative at a particular point, you will have some sign. So, if you get a positive derivative, the dependent variable is increasing. And if you get a negative derivative, the dependent variable is decreasing, right? And after finding all this, describe your answer in words. To that context, we have to explain. So we should not say the dependent variable is positive, so that it is increasing because we have a positive derivative. This won't work. So we have to describe in words, and that requires a little practice. And here is an example. The height h of t of a ball thrown vertically is modeled by h of t is minus 5t square plus 20t plus 30. But t is time in seconds and h of t is height in meters. Now interpret h of 2. Let's solve. Very simple. Just plug in 2 in the given function. Right? So write your function and plug in 2. You got h of t as 50 meters. Right? So interpretation is important. I got h of 2. But what does it say? When your time is, when you plug in time 2, you got the height 50. So the interpretation here is the ball, right? The ball is 50 meters above the ground at t is equal to 2 seconds. So when you plug in 0 or any other value, it will give respective position of the ball. So it should be a position. Yeah, you can say even the position of the ball is 50 meter above the ground. So this is just a position function, right? And next one is interpret h dash of 2 and h dash of 3. Let's solve this. We have h of t. You know how to find the first derivative. So h dash of t is just apply power rules and you got minus 10t plus 20. Then plug in the value h dash of 2 and simplify. You got this. H dash of 2 0. And h dash of 3 again simplify. Plug in and simplify this. We got minus 10. Now it's time to interpret. I got h dash of 2 is 0. The first derivative at when time t is equal to 2 is 0. Okay, first derivative tells us the velocity, we can say, or the rate of change of the position of the ball, right? So here we can see 0 means the best way to interpret the velocity of the ball at t2 second is 0 meter per second. This means the ball reaches its peak point, right? So when it is at peak, it will be momentarily rest, right? Initially it will be on rest, finally it will be on rest, and in momentary rest means it will be moving, suddenly it will go to the peak point. So that's what it represents. And interpret h dash of 3, I got a negative 10. Okay, so it is a velocity. Velocity is negative. The velocity of ball at t equal to 3 second, third second is minus 10 meter. This means the ball is falling due to the gravity at a rate of 10 meter per second. So if you say falling, you are interpreting the negative sign over there. So no need to mention it here, right? That's the interpretation example. Now, interpret h double dash of 5. Let's find. We have h dash of t. So write that and find h double dash of t, which is minus 10, which is a constant. Whatever you plug in, it's going to be minus 10. So let's interpret this. This means the acceleration of the ball is constant throughout, right? And you got a negative, so better you say deceleration or downward acceleration, right? So the ball experience a constant also we are mentioning because whatever point you are plugging in, it will be the same minus 10 throughout its motion. So the ball experiences a constant downward acceleration of 10 meter per second square, and this is the unit, right? So the height function is meter, rate of change, meter per second, rate of change per change. So meter per second is meter per second square. And this is very important, the unit is, right? And moving to the next. Straight line motion connecting position, velocity, and acceleration. We already did an example, right? So let's try to connect and what is a straight line motion and what are the things we should take care. Let's go. Let me share the screen with you. Okay, here I have taken, this is the object and displacement function is given. So the object, it's exactly like what we did. It's moving up and coming down. Now let's sketch the velocity. So if I ask you what is the position of the object when t is 1 second, so we will just say this at first second, it's somewhere here. You just stop at first second. Okay, it's something over here. It's nearer to 10, right? And when it is, so this is the peak point, somewhere in between 1 and 2. And it again come to the rest. This is the position. This is how the object is behaving here. Now let's compare the velocity. The velocity is something downward, right? So let's play this. So when your object is like at 0.5 seconds, object is at this place, like it can be interpreted as 8, and the velocity is something over here, right? And after this, so exactly at the peak point, the velocity is 0. We say velocity is momentarily at rest, right? And then it continues to drop down and the velocity also going below the x-axis, right? So the negative values. So this is the velocity interpretation. When velocity is above x-axis, your function, the object is increasing. And when your velocity becomes 0, it's momentarily at rest. When it continues to drop down, your velocity become negative, right? And let's go with acceleration. And we see the acceleration is constantly negative 10. So that's what happens. Whatever you do, right? The velocity is going to be, the velocity is changing with respect to the position, but the acceleration is same. So it doesn't have any altering. There is no rate of change in the acceleration. It's same negative 10 throughout, right? And this is an example. Now, moving to the content. Now, position is S of t, means it represents the location of object at any time t. That's simple. And velocity can be written as S dash of t or especially V of t. And what does it say? It represents how fast and in which direction the object is moving. It also the direction it will give. We know the sign conversion, right? So that. And acceleration is S double dash of t. This is acceleration actually. And it is S double dash of t, V dash of t we can say, or A of t, right? And it represents how the velocity is changing over the time. Velocity rate of change, displacement rate of change, right? And unit is important. If this is in meter and then this is in meter per second, this will be in meter per second square, right? Now, velocity rate of change of position. Now let's, when my velocity is 0, less than 0, greater than 0, what happens? When your velocity is less than 0, the particle is moving left or down. So when the object is moving horizontally, we can say, oh, it's moving left. Or when you're considering a vertical motions, then you can say it's going down, negative. So it's very simple. Left means negative, downwards, right? And if it's greater than 0, it's moving right or moving up. And if it's equal 0, it will be at rest. That's simple. Now, average velocity. Yeah, it's same. S of b minus S of a by b minus a. So for this average velocity, you need a position function on the interval a comma b. So you know the position function S of t. You want the average between the time stamps a and b. So you have to work on it. Just a slope formula, right? And speed is just modulus of the velocity. Find velocity and you take a modulus because speed is positive, right? That's why. And now, next question is it speeding up or slowing down? So at a particular time, I want, is my object speeding up there or is it slowing down? The acceleration we are talking about, right? So to find that, the velocity and acceleration have same sign, the particle is speeding up. We know how to find velocity and acceleration at a particular point. If they have same sign, they are speeding up. If they have a different sign, they will be slowing down. That's simple it is. So you can interpret using these techniques. Now here is a quick example. The time is given, respective velocity and acceleration is given. We have to make the conclusion. So the conclusion is it speeding up or speeding down? That's what alone we are going to do. And they have different sign, right? Velocity positive, acceleration negative. So different sign, slowing down. Again, velocity negative, acceleration positive. So acceleration positive means you should not say, oh, it's positive, something is speeding up. No, it's slowing down. It depends upon both the signs, right? It's slowing down. And next to velocity and acceleration is positive, so speeding up, then both negative is speeding up, right? So this is all about. Now, distance and displacement. Distance means you're traveling from one object is traveling from one point to other point. What does it cover? The total distance covered by it. Whatever direction, that doesn't a problem. Displacement is something, the net change, the shortest distance between start and end point. So if you are starting here, if you're going here, so we can move like this. So the distance travel is like, we can say it's 50 kilometers. But displacement is you're here at, and then you travel this much. But direct distance from this, the shortest distance between short and end points is what displacement is. So they have a huge difference. And now let's solve an example. A particle moves along a straight line and its position at time t in seconds is given by the function. We are going to interpret all of this: displacement, velocity, and acceleration. First, what is the displacement of the particle between 0 and 3? Displacement is just s of t, right? So displacement is s of 3 ending point minus initial point. S of 3 minus s of 0, just plug in our function. S of 3 minus s of 0. Just simplify those, you got a 0, right? So what we need to interpret this. The displacement is 0. What does it mean? The particle returned to its starting point after 3 seconds, right? When you do it for 4, it might show something else, right? If you got a negative 3, so from the starting position, it is like, if you got a negative 4, okay, it's 4 meters left of the starting point, right? Now, at what times the particle is at rest, determine the velocity of the particle at t equal to 1 and t equal to 4. What do these velocities indicate about the direction of motion? Okay, let's solve the first one. At what times the particle is at rest? Rest. What we see? V of t is 0, right? So very simple. V of t means you just differentiate the s of t. S dash of t, just apply the power rule, and this is your V of t equate to 0 and solve for your t. We got t is 3 and t is 1. So when time is 1 and 3 seconds, the particle is at rest. That's simple. Now, determine the velocity of the particle at t is 1 and 2. Okay, we already got something here. At t equal to 1, the velocity is 0, right? So, but still, you have the velocity function, plug in 1 and 2. 0 and minus 3 seconds. What does it they say? When it's 0, the particle is at rest. When it's minus 3, I hope you remember, velocity is less than 0 means it's to the left, right? So the particle is moving backward at 3 meters per second when time t equal to 2. Here we don't know whether it's a horizontal motion or vertical. So you can say backward. It's going backward at 3 meters per second speed when time is 2. That's simple. And acceleration, speeding up or slowing down. Very simple. And here we depend on velocity also. We already have velocity at time 1. So find acceleration. So differentiate the v of t. We got it. And a of 1, acceleration at 1 and acceleration 2, we got it. Now compare. Velocity at 1 at 2 seconds, acceleration at 1 and 2 seconds. Now, for the part A, you have to say at t equal to 1, velocity is 0 and acceleration is negative 6. We know if they have same sign, speeding up, different signs slowing down. But this first one, the particle is slowing down and reversing the direction. Okay, 0 means, okay, should I take it positive or negative? So in that case, there is a change in direction, right? So the particle is slowing down. Of course, you can take the acceleration sign. So the particle is slowing down and its reversing direction is the very important interpretation we have to give. And second, at v equal to 2, negative velocity and 0 acceleration. So in this case, velocity is negative, so it's moving backwards, right? So at t is equal to 2, the acceleration is constant. Okay. The acceleration is constant over here, right? And rates of change in applied context other than motion. So yes, population growth, temperature change, and spread of disease. These are the some common examples, and we have a lot more. So main thing is the first derivatives gives your rate of change of quantity in that context. And the second derivatives helps you interpret how the rate of change is itself changing, right? Now here we have an example. The temperature of a cup of coffee is modeled by the function. T is temperature in degree Fahrenheit and small t is time in minutes after the coffee is poured. We have to find this. Find the rate of change of coffee's temperature at t is 5 minutes. Interpret the meaning of first derivative. Determine whether the temperature cooling is faster or slower. First, okay, it's quite easy. We can use Desmos for this. So let's go there. I'm sharing the Desmos screen to you. Okay. First, you give your function. This is my function. Actually, they give in t of t form. T means f here, and you just use the variable convention, okay? So this is my f of x. And actually, the first question is the rate of change of the first rate of change. So first derivative, you have to find f dash. So after finding, you just plug in f dash of x, you will get the gradient function here. And I need the rate of change at when the time is 5 minutes. So t equal to 5. Here x is 5 actually. And this is what this. Let's make this into, right? Negative 7.278. At t is equal to 5 minutes, this represents rate of change. So minus 7.278. That's simple. We can do in seconds. I will say in 30 seconds, you can solve this with the help of Desmos. And interpreting. At t equal to 5, the coffee is cooling because we got a negative, right? In our Desmos 1. So minus 7.277 something we got. And we are rounding up. So it's cooling down, right? So that it have a negative. So it's cooling at a rate of 7.28 degree Fahrenheit per minute. And unit is also very important, right? Interpret the meaning of first derivative. First, you find the first derivative. T dash of t is write t of t and differentiate. 70 will become 0. 120. Copy the function and multiply by whatever is there inside. So 0.1. When you simplify this, you got negative 12 into e power. So this tells us how fast the coffee is losing heat, right? So the temperature will be cooling down. So that is what T dash of T tell us. And the unit is degree Fahrenheit per minute. Determine whether the temperature is cooling faster or slower at T equal to 5 compared to T is 10. So temperature is cooling faster or, okay, cooling down, but is it faster or slower? In that case, we have T dash of T. We are comparing the rate of change of the change, how the rate itself changing. So T double dash of T, differentiate it again, we got this. And find T double dash of 5, just plug in, you got this, which is greater than 0. Sign convention is important. And T double dash of 10, that is also positive. Let me compare the numerical value. T double dash of 5 is greater, right? Is greater than T double dash of 10. So we can interpret the coffee is cooling faster at T equal to 5 than T equal to 10. So greater, it's faster cooling. Lesser, it's slower cooling. So that's what we can interpret the comparison over here, right? And that's it. Now, we are into 4.4, Introduction to Related Rates. It's very simple. Let's see. Related rate problems involve finding the rate of change of one quantity in terms of rate of change of another quantity. It's not always, okay, distance and time, velocity, acceleration, right? One quantity will be changing, the other will also changing accordingly. That is what related rates. And this happens when two or more variables are connected by an equation. And mostly we will deal with the variables will change with respect to time only, right? And for example, this is, you can imagine as a balloon and its radius is 2. Its volume will be something x centimeter cube. When you increase the volume, right? It's a balloon. If you inflate it, the radius will change. Like if you're inflating, you're changing the radius, then volume also will change. They are relatively changing. It's not like 2x, 4y. They have some relation in between. So we will be solving these kind of problems. That is what related rate is. One variable will be changing. Relatively, the other variable will also get affected. Like here, radius and volume, right? Now, how to solve these related rate problems? First, you sketch the diagram, understand what is the situation and sketch a neat diagram on it. Then identify variables, which is like lot many variables there. Try to make it into two variables. Then relate variables in an equation, connect them in an equation. Even if it's implicit, that's completely okay. And differentiate with respect to time t. Okay, you differentiate. We know implicit differentiation, normal differentiation. Do that. Then plug in known quantities. You know this step is very important, right? So differentiate, then plug in. Then interpret solution with the appropriate unit, right? And very important thing, do not plug in non-constant quantity before differentiating. If something is not a constant, don't just plug in over there. Okay. Here is a simple example. A ladder is leaning against a wall. The bottom of the ladder is being pulled away from the wall at a rate of 0.5 meters per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 3 meters away from the wall and the ladder is 5 meters long? Okay. Um, the ladder is leaning against. You are pulling the bottom. So if you're pulling the bottom, the distance between the wall and the bottom end of the ladder will be increasing, and the top and the bottom of the wall will be decreasing. Okay, there is two changes relatively. Some information are given. Let's make a sketch. So this is the ground and this is the wall. This is your ladder initially. Okay. Now you are pulling down, like the bottom of the ladder is being pulled. Okay, if I pull it somewhere over here, what happened? Its position is changing. This is changing. X is changing. Respectively, Y is also changing. Right? And let me do more. So X is becoming like still what before X. Now it's X is changing like this and Y is becoming shorter. Yes, we can understand this. But ladder side will never change. It's the same ladder. We are not breaking it. So the ladder's length is constant here. And X and Y are changing, right? So let's make this the diagram. So we just visualize what had been done over here. So let it be X and this is BY. Of course, they are changing. It's not a constant X and Y. Now let's write the equation because it's a perfect Pythagoras theorem, right angle triangle. So if this is X, Y, and L, you can make an equation. And yes, the length of the ladder is a given. The ladder is 5 meters long. So you can plug in. X square plus Y square is 25. We can do that. And what else they have given? The bottom of the ladder is being pulled away from the wall. So where you are pulling the X and that is being done in this rate, 0.5 meters. So dx by dt is 0.5 meter per second. And X is equal to 3 is how fast is the top? We need, when this distance is X, right? What is the rate of change of Y? So when X is 3, what is dy by dt is what we need. Okay. And one more thing, I need Y value, right? When X is 3, what is Y? It's simple. Make the right triangle. When X is 3, I know ladder is fixed at 5 and Y. Just apply the Pythagoras theorem or you can use the Pythagorean triplet. It's 4. So we got that. Now, this is my equation and differentiate it first. 2x, x square. And here you should not say, okay, it is just x. So normal differentiation. We are differentiating with respect to time t. So 2x dx by dt is important. 2y dy by dt and 25 will become 0. Now plug in the known values. X is 3, dx by dt is at that moment this is the rate of change. Y is 4. When you plug in all this, your only missing thing is dy by dt. That's what we are trying to find. So simplify this. You got dy by dt is minus 3 by 8 meter per second. Okay, now interpretation time. The top of the ladder is sliding. Y means this is the top of the ladder is sliding down the wall at the rate of 0.35. Since I mentioned down, I won't use the negative here. Right? I will just write the rate, the magnitude alone. So this is a simple example of related rates. Right? And that's simple. Now 4.6, approximating values of a function using local linearity and linearization. It's very simple. If you remember in our one of our units previously, differentiability means this is my function. Is it differentiable at this point? You will zoom in over there. And if it looks like a straight line, yes, it's differentiable. So this is how we are going to deal with this. Linearization. Linear means kind of a line, right? So it's similar to that. The tangent line of f of x at x is equal to a can give approximate value of f of x for points close to x is equal to a, right? Um, so for example, you have a curve here and you need what is the value of your function at this point. You just draw a tangent line and you find the value of the tangent line at this point. That will be an approximation of this f of a, right? So concave down and you're drawing a tangent line. You need a point here. You draw the tangent line, right? This will give an approximation and it is called overestimate. Actually, if you need this value, you will plug in the tangent function, but it will overestimate it. The value it will give is over here, but you need is this value. So this is overestimate. So concave down and you are applying the linear approximation using the tangent line, it's overestimate. And for concave up, this is my point I need. What is the value of the function at this point? So you will draw a tangent at somewhere over here. And you will plug in this. And this will underestimate. Actually, your value is something here, but you will get the value of this. The approximation will be closer, but it will be an underestimate. Got it? Now, a simple example. F is concave up on its domain. F of 4 is 5, f dash of 4 is 3. What is the estimate for f of 3.8 using the local linear approximation of f at x is 2? Is it an underestimate or overestimate? Very simple. You first find a tangent line. Because it's my curve, you find a tangent line at x is equal to 2. Okay, x is equal to 4, actually it is. At x is equal to 4. You have the information to find the tangent line. Then at 3.8, what is my function value? Very simple. Just plug in 3.8 in this particular tangent value, right? First tangent line, this is the equation. Actually, tangent line equation is y minus f of a equal f dash of a into x minus a. These are all the things given to us. Like your a is 4. So y minus f of 4, f dash of 4, x minus 4. And f of 4 is also given to us. 5 and f dash of 4 is 3. And that's what we are plugging in. Y minus 5, f dash of 4 is 3 and x minus 4. And just simplify it, right? So this is your tangent line. And you need to approximate f of 3.8, right? It is. So estimate f of 3.8. And you just plug in 3.8 in your tangent line equation. F of 3.8 is 3 into 3.8 minus 1. It's 4.4. And it's an underestimate because it's concave up and your tangent line, of course, will be here. And sure, it will be an underestimate. Actual value here, but you will underestimate it. That's simple. We have another approach for the linearization. L of x is f of a plus f dash of a into x minus a. This formula also I can use. L of x is linear approximation function. And f of a, value of function at the point of tangency. And f dash of a, derivative at the point t. So this example, use local linearization to approximate root 26. Okay, what is the function? The function is root x. And you write the linear approximation formula. And a is equal to 25. This is the closer point I can choose, right? And find f of a, f dash of a. This is what we need. So f of a is 5. F of 25, which is 5. And f of x is x power half. F dash of x is 1 by 2 root x. Find f dash of a and plug in over here, right? This is what, when you plug in, you will get it. We are finding the linear approximation at 26, square root of 26. So now you can replace your x with 26. And that will give you 5.1. When you use calculator, you got something here. Yeah, the approximation is very closer. And we did an overestimate, right? So that is what linear approximation is. The last topic here is L'Hopital's rule. How to use it and when to use it. And some essential examples I'm going to solve here. So this is basically for indeterminate forms. Indeterminate and undefined. Undefined means we know it's not defined over there, but indeterminate is something like this. We can't make a decision here. Okay, is it a point or we can't define? So we can't make any decision. That is, these two are important forms, 0 by 0, infinity by infinity. For these cases, we can use L'Hopital's rule. So the rule is limit x tends to a, f of x by g of x is limit x tends to c, f dash of x by g dash of x. What we did, it's a again. We applied the limit, but instead f of x, g of x, I use the derivative for the respectives. That is all about L'Hopital's rule. The condition is we have to do the direct plugging in first. The limit must initially result in indeterminate form. In that case, we can use L'Hopital's rule. And both f of x and g of x is differentiable at the point x is equal to a. The derivative for this must exist. Then yes, we are good to go. Here, so these are steps. Verify the indeterminate form by direct substitution. Then differentiate the numerator and denominator, and don't use, like, since we use the two function, don't use the quotient rule. It's not the quotient rule. Differentiate them separately. And step 3, reevaluate the limit at the same point. And again, if you got an indeterminate, you can repeat the process until your limit is resolved. So you can do a number of times. Now this is first example. Limit x tends to 0, sine 5x by x. So the solution will go like this. Direct plug-in. You got 0 by 0, which is indeterminate. Okay, I will take a L'Hopital's rule. What does it say? Differentiated. Limit x tends to 0, sine 5x is cos 5x times 5. Right? Chain rule. The next differentiation is 1, which is 5 by 1, which is 5. Right? So we got the limit as 5. That's simple. And then you have to so this will be 5 over here. Right? Then other determinant forms, 0 into infinity, infinity minus infinity. These are also other indeterminate form. But if you got this, we won't apply the L'Hopital's rule directly. But you can convert into either 0 by 0 or infinity by infinity form. One example I will show. Evaluate x tends to infinity this function. So first you will direct plug in whatever it is. And I got root of a very big number minus infinity. It's infinity minus infinity. And don't say infinity minus infinity is 0. No, it is not. It is indeterminate form. In this case, you can simplify the expression. So first write the expression and multiply. Whenever you see the root, kind of a surd, you do the conjugate. So I'm going to multiply with the same things with the opposite sign and divide by it. And simplify it now. A minus b format you can apply. A minus b, a plus b is a square minus b square. And simplify it furthermore. You got this. Simplify it furthermore. You take x common. Try to cancel out all the common stuff with numerator, denominator. Utmost simplification. This is what we got. Now you reapply the limit. X tends to infinity. 1 by infinity. Because your approaching limit tends to infinity, 1 by infinity, we know it's 0, right? So limit 1 by n, n tend to infinity is 0, the same thing. So now you got square root of 1 plus 0 plus 1. Square root of 1 is 1, 1 plus 1 is 2. And that's how, even though it is not in the, what we call, the desired indeterminate form, we convert in that form, right? So that's it. With the L'Hopital's rule, we are coming to the wrap of this video. I hope this video might be helpful to you. And if you feel that helpful, you can share, like, and subscribe to us. And I will be meeting you in another unit with interesting questions and the concept review. Until then, keep learning and keep practicing. Thank you for watching.